to identify the important intermolecular forces in pure compounds, we've got to look at the structure of the compounds and decide whether they are polar or not. If they got bond dipoles, they may have dipole-dipole interactions. If they've got oxygen, hydrogen, nitrogen, hydrogen, or fluorine hydrogen, those dipole-dipole interactions could be hydrogen bonding interactions. And then we're going to look and see if they are polar molecule or not to determine whether there's any dipoles. If we don't see any dipoles at all, if there's no dipole moment, then it's probably going to be dispersion forces only. So remember, dispersion is going to be temporary dipoles from the electrons just literally being wherever they're going to be, and that particular split second they could be on one side of the atom or another. Dispersion forces are, generally speaking, the weakest kind of intermolecular forces, but they are displayed by everything. They are proportionate to molar mass. More electrons means greater dispersion forces. Also, the shape of a molecule matters. Higher dispersion forces are associated with like longer, more spread out molecules, because at that any given temporary instant where electrons are not symmetrically distributed in a long chain molecule, that effect will be exacerbated. There'll be more difference in polarity than in a more compact ball spherical type molecule. So we've got dispersion forces that are temporary dipoles, dipole-dipole interactions between permanent dipoles. So that's where you see a difference in electronegativity when you're drawing the Lewis structure. So you know you have a polar bond. So we call that a permanent dipole because it's there all the time. And then hydrogen bonds is a specific subset of dipole-dipole interactions between oxygen, hydrogen, nitrogen, fluorine, fluorine, hydrogen, and neighboring very electronegative atom, oxygen, nitrogen, or fluorine. Can mix and match. Okay, so if we look at these, and you may have to draw the Lewis structures to be sure that you understand what's going on here. Silicon tetrafluoride. So if we look up silicon and fluorine and draw the Lewis structure, you're probably going to come up with something very symmetrical that's looking a bit like this. Not going to worry about putting the bonds in there. The fluorine silicon bond is well, it's going to be highly symmetrical, right? So I'm not quite sure how polar silicon is off the top of my head. I know fluorine's very electronegative, so perhaps we should just check that real quick. My table of electronegativities. Ba, 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 ba. Right, so looking at the numbers, I would determine that the silicon-fluorine bond would be polar, right? Because I know fluorine's like super duper electronegative, it's about 4. I looked up silicon and it's like 1.9 something, so I would say it's enough for the silicon-fluorine bond would be polar. But of course, you've got to also look at the molecule overall and see if that bond polarity cancels out, which it does, because remember, this is actually going to be a tetrahedral shape if we use VSEPR theory, right? Steric number of 4, and the directions of those silicon fluorine bond dipoles are all going to cancel out, right? So the molecule as a whole has no net dipole moment. So I would go ahead and say that that is dispersion only, no dipoles. Nitrogen trifluoride, if you go ahead and draw the Lewis structure, is going to be very similar to ammonia in terms of shape. Obviously, the fluorine has lone pairs on it. The hydrogen does not. So we will end up with something a little bit like this. So definitely polar, right? Nitrogen fluorine bond is polar. In fact, is my favorite flavor of dipole-dipole interaction. That NF bond is super duper polar, but it's not enough to be hydrogen bonded, right? Because that is a fluorine, not a hydrogen. So it's still very polar, but there's dipole-dipole interactions, not hydrogen bonding. And of course, we mustn't forget that we always have dispersion forces, regardless of if we have dipole-dipole, hydrogen bonding, whatever. If I draw ammonia, so again, it's going to be an analogous structural shape, right? So in terms of VSEPR3, for both of these, the steric number is 4, 3 bonds and 1 lone pair. So they have a tetrahedral parent shape, but of course, the lone pair counts towards the molecular shape, but then we don't name it as a tetrahedral shape, we only name the bonds. So that would be trigonal pyramidal, right? So just like a triangular base pyramid would be the actual shape of that. So ammonia, of course, has NH bond, so that is a particular subset, hydrogen bonding, dipole-dipole interaction, because hydrogen bonding is a dipole-dipole interaction, and dispersion. And then if we were to draw the iodine molecule, again, it's just going to have a Lewis structure like this. Of course, iodine has lone pairs all around it. I guess I could try and put those in. Come here, you. All right, so gonna spread this out a bit. Sorry to do this quickly. It's kind of gonna just be a bit like these should be one on top of the other, but not side by side. But I'm going for speed and efficiency. Okay, so this would be what the iodine diatomic iodine would look like. So again, two atoms, the same identity, completely non-polar. Okay, so the only possible intermolecular forces is dispersion forces. All right, so I hope that is at least a little bit helpful for you in squirreling this out. Okay.